Alrighty, good afternoon. Hopefully the orientation for everything isn't too hard to read. I have a strange setup going on. So this is going to be an explanation of the tides from our book. This is section 9.2 that the book touches on. And to start with, it goes over, the first thing the book denotes is assume that the earth is covered in water instead of continents. It actually just makes it easier to discuss the tides overall. And the book has a great figure, which I tried to draw myself, and it didn't turn out too well. But on the left here, we have what is a common misconception of the earth if it was covered in water. The blue is supposed to be the oceans, and you can see how the moon is pulling the oceans towards it. But what actually happens is the case on the right, where it's a more elliptical shape on the ends, and the poles themselves, north and south being, actually have much less water than the east and west. So, because of this, we can come up with we can use this equation discussed in chapter 9 of mr double dot equals F minus ma. And gravitational pull is also denoted there previously in the chapter. So what we need to solve this is we need to figure out what A equals. So to do this, there is a good diagram which I've reproduced here that shows some of the angles between the Earth and the Moon. And we have our gravitational pull over here, and it's very similar. As you can see over here, we have our G, and m sub m is just the mass of the Moon. And then we have our vectors from the Moon to the origin of the Earth. We have our x and y, and the line coming out to the edge of the Earth right there, that m is simply the mass at the point of the surface of the Earth, which in this case would be where the oceans would be. Now, the d is just the position of the object relative to the Moon. So whether that would be in this case it would be the oceans is what we were discussing. So from there, we can now plug our A into our equation, and it gives us this somewhat nightmarish looking thing. But it's not too bad. Fng is simply the net non-gravitational force. You can see down there at the bottom. And whenever we denote our forces into Fng and F tide, we get a much nicer looking equation for m double r, or r double dot, which comes down to just mg plus the tidal force and the net non-gravitational force. So from here, we need to go and figure out what the tidal force is. And we have written it down as this force over here. Notice that the negative sign stays. So from here, we just need to go and find the magnitude of the thing. And we know that both mg and the tidal force are going to be conservative. And knowing that means we can write the gradient of the potential energy. So we have right here, we have mg equals the negative gradient of the potential energy of Earth's gravity, and then we have the negative gradient of the tidal force. So using the tidal force from what we got earlier, we can denote that this is what our potential energy would be for this tidal force. And we can draw this lovely diagram. Again, these are also in your book. They found someone much better at drawing than me to do these, luckily. But this will help us figure out our vectors and find the actual total tidal force and the displacement caused by the Moon. So we have our point Q, P, R right there. And notice that D naught is simply the distance from the center of the Moon to the center of the Earth. And R is just the radius of Earth, if you can believe it with that drawing. So now we can make the equation that UP equals UQ, which is pretty important to note. Because of that, then we know that both UP and UQ are made up of their respectable EG and tidal force components. So when we write that out and put them on the respectable sides, this is the equation that we get up here at the top. And then one thing you should recognize is EG is just the conservative force of mg, and we know that conservative force is just mgh. So knowing that, we can simply denote that UEGP minus UGE Q is just equal to mgh. So now we can look at point. So now we need to find UQ and UP tidal forces. So at point Q, bring up our drawing again, we can see that D is actually it's actually just the vector with D naught and R. So that can be, the magnitude of that is simply D naught squared plus R squared under square root. And we know that R is actually just the radius of Earth, so we can just write that as there. And we see that X is also 0, since might be difficult to see on this picture, but we're setting our origin at the center of the Earth. So X is 0 for point P, or for point Q, excuse me. So now with this, we can revisit our expression for U tide of point Q, and we can plug in our newfound D, and it gives us this. And now this is somewhat ugly, so we need to rewrite it. And this is something we've done before all in class. It's not too bad. And then we have to do a binomial approximation, and that's very easily achieved because the radius of the Earth and divided by the distance between the Earth and the Moon is much, much less than 1, or it's an extremely small number. So we can just assume, using this binomial approximation, that we can just write our U tidal force as this expression down here. And once again, this was the point, the diagram I was mentioning. All right, so now we have our tidal force at U. So now we need to get our tidal, or not force, our tidal potential energy for U. And now we need to get our tidal potential energy for point P. So this is actually quite similar to the tidal force of Q. You can see the sign is switched, and that's mainly because if you look over here at our graph, D in this case from point Q is D naught minus RE, and X is no longer 0. It's no longer at the origin, so it is actually RE. So this does change things a little bit, but it still cleans up to be quite nice. And now we can go back to look at our equations of potential energies that we touched on earlier, and we know that this left-hand side is simply mgh, because that is the gravitational mg potential energy. And then now we have each of our tidal forces for point Q and point P. So we can plug that in, and it ends up coming down to this. It's not too crazy, but one thing that we learned in Chapter 9 is that G is simply Gme, in this case, Re squared. And so from there, we can actually simplify it further and solve for H, which comes down to this. And now that we have our H, our H is actually going to be the amount of tidal shift, if you want to call it that the oceans would experience due to the gravitational force. So the only thing of note is this is only with respect to one mass other than Earth. So in our particular case, that would mean this one is written with the respect of the mass Moon. So we would have to, if we solve this for H with constants, which is what we're about to do, it would only give us the amount of tidal shift that the Moon caused on Earth. So these are a bunch of constants given to us by our book. When you plug them into the equation, it all cleans up nicely, and we get 54 centimeters. Now, like I said earlier, this is what the Moon alone causes. So this is not the total tidal movement that happens in the Earth, on the Earth. So we also need to find the H with respect to the mass of the Sun. And that's pretty simple. We just replace the mass of the Moon with the mass of the Sun, and we need to change our D naught, which remember, is just the distance from the moon to the center of the earth to the center of the moon, to the center of the moon to the center of the sun. And that is this expression here, 1.495 times 10 to the 11th meters. And then we plug all this into our equation, and we get a height of 25 centimeters. So the moon is actually more than twice as impactful on our tides than the sun is. But then we can calculate the total amount that both gravitational entities pull on the Earth, and that comes up to, it's just the moon and the sun added together in 79. Now, the reason that they're added together is this is assuming that if we have our Earth here, we have our moon here, and then we have the sun here. So that they're actually just lined up and both pulling in the same direction. They're not pulling at angles or anything like that, which just makes it nice and easy for calculations. But that is it. So if they were also, the other thing to note is if they are on opposite sides of each other, say the moon is over here and the sun is still over there, then it would simply be the shift that the moon pulls minus the shift that the sun pulls would give us a different h. So that would just be hm minus hs for our h value. And that was all I had to share with you guys. So hopefully this was somewhat informative and able to follow along. Hopefully I didn't skip over too much. Good luck on the final.